So recall that in the previous lecture we had proved this nice result. So in the previous lecture we proved that SON is connected. So before we proceed, let me make the following remark. So if we replace, so using the same, using the same methods or using similar ideas, we can also show that SUN and UN are connected. So recall, what is SUN? SUN is all those complex matrices, complex and cross-end matrices, such that A star A is equal to identity and determinant of A is equal to 1, and UN is all those A in MNC which have only the first condition, the unitary matrices, right? So just as in case of SON, we define this map to Sn minus 1. So for UN, we define this map to S 2n minus 1. So so here a matrix A gets sent to the first column. Yeah. Now the inner product AE1 comma AE1 is equal to, so in the case of UN we use the standard metric, standard inner product on Cn, which is given by V comma W, is defined to be W star V, and recall that W star is equal to W transpose conjugate. So we have a column vector and we take its transpose and conjugate all the entries. So this, with this definition, this inner product is going to become AE1 star AE1 which is equal to E1 star A star AE1, and since A star A is equal to identity, because A is in UN, there is going to be E1 star E1 which is equal to 1, right? But also notice that the columns, the column of A, the first column, consists of complex numbers Z1, Z2 up to Zn, right? And if each of these Zi, if I write it as Zj, if I write it as xj plus iyj, right, where xi comma xj comma yj are real numbers, then this implies that since the inner product is 1, this implies that summation mod zi square is equal to 1, which implies that summation xj square plus yj square j equal to 1 to n is equal to 1, which implies that we actually get an element of AE1 can be viewed as an element of S2n minus 1. Okay, so let's call this map. Okay, if we call this map psi, and we call this map phi. Yeah. So over here we prove that in this situation we prove that phi of A is equal to phi of B if and only if B inverse A belongs to, is a matrix of this type. There is something in S1 minus 1, right? So here we will have to prove that psi of A is equal to psi of B if and only if B inverse A is equal to is in 1 0 0 un minus 1, right? And then the base case, so the base case for the induction will be U1, which is, you can easily check, is homomorphic to S1, which is connected. Right? And similarly, the base case for, so in the same way we can define a map from SUN. So we, again, let me call this psi 1 S2n minus 1. Once again, this map is A goes to AE1. Right? And here the base case for the induction will be SU1, which is simply 1, which is connected. Okay, so so the details are left as an exercise. Okay, so having said this, let us begin with today's lecture. So today we will start our discussion on compact metric spaces. So basically we are going to, so the main theorem of this lecture is the following: let X be a metric space, then X is compact if and only if every sequence in X has a convergent subsequence. So let us prove this. First, let us assume that X is compact. Okay, and suppose we are given a sequence X n where n is greater than or equal to 1. So we are given the sequence of points, and we want to show that S has a convergent subsequence. So let this be a sequence in X. Okay. So if S is finite, so if the cardinality of S is finite, so then there is some, or yeah, so there is some X in Xn in S such that X is equal to Xnj for infinitely many nj's. For infinitely many indices, right? So and then so we can take this subsequence, right? So this subsequence, in this subsequence, every element, all the elements are the same, and therefore obviously it converges. So let us assume that cardinality of S is infinite, right? So we may replace S by a subsequence of S. So since we may replace S by a subsequence of S, so we may assume that all elements of S are distinct. Yeah. So the cardinality of S is infinite, so therefore we can find a subset which is infinite and which contains and each member of that subsequence is all the members of that subsequence are different. So if you can find a subsequence of this subsequence which converges, then we would have found a subsequence of S which converges. So we can assume this. So let Y be the closure of S in X. Okay. So if S is a set of points like this, and if Y minus S is non-empty, that means there is some point x naught in Y minus S, right? Then there is a point x naught in Y minus S, right? And as x naught belongs to S closure, this implies when we take any neighborhood of x naught, b 1 upon n x naught, intersection S is not empty, right? And this implies that there exists a sequence of xn in S such that xn converges to x naught, right? So we are done in this case. So we are done. So if Y minus S is non-empty, then we have found. So let me say there is a sequence Ym, because Ym such that Ym converges to x naught. Okay. So then we have found a subsequence in S which converges. Okay. So let us assume that Y minus S is empty. So note that S is always contained in S closure, which is equal to Y, and Y minus S is empty implies that Y is equal to S closure, right? If xn so if xn is any point in S and there is a subsequence in S converging to xn, then we are done, right? So for instance, we can take a sequence like this, and this sequence may converge to this point xn over here. Yeah. So let's assume that. So thus we may assume that for every there is no subsequence in S which converges to xn. In other words, what this means is for every x, for every xn, there is a small neighborhood. So for every xn, in other words, In other words, for every xn, there is a neighborhood B delta n of xn such that B delta n of xn intersected S is just this xn. Okay. Okay. So now, as Y is S closure and this is equal to S, this implies S is a compact, is a closed subspace of a compact space. Of a compact space. Right? Recall that we had assumed X is compact, yeah? So thus S is compact. Closed subspace of a compact space is compact, right? However, we may write S as the union over n greater than or equal to 1 B delta n xn intersected S, right? This is xn, right? This is simply equal to union n greater than or equal to 1 xn, right? Yeah, this shows that S has an open cover which has no finite subcover. Which is a contradiction. Okay. So, so this completes the proof of one part. So this shows that S has a convergent subsequence. Okay. So now let's prove the converse. So to prove the converse, next we prove the converse. So let us assume that, so suppose every sequence in X has a convergent subsequence. Yeah. So we shall show that X is compact. Okay. So for this, let us begin with an open cover, B an open cover of X. Right. So our aim is to construct a finite subcover of this. Okay. So we make a claim. There is a delta greater than 0 which works for all X. Such that when we take this open set B delta X, right? So we are given our space X, and this has an open cover, right? So no matter which X we choose, when we take this ball of radius delta around X, it will be contained in one of the UIs. Yeah, is contained in UI for some I. Okay, is completely contained in one of the UIs. So let's prove this. So prove claim 1. Okay. So if claim 1 is not true, right, then for each, so no matter how small we take delta, there will be an x such that the ball of radius delta around x is not going to be contained in any of the ui's, right? So for each n greater than or equal to 1, there is an xn such that we take b1 upon n xn is not contained in ui for any I, right? So let us take S to be the sequence of xn's. Okay, so then there is, by our assumption, there is a convergent sequence, a convergent subsequence xnj, and let's say this converges to some x naught in x. Okay. So there is some u naught such that x naught is in u naught in our open cover, and for this u naught, yeah, there is an epsilon positive such that this ball of radius epsilon around x naught is contained in u naught, right? So our u naught could be this, and our x naught could be somewhere here. This could be our u naught, right? And this ball of radius epsilon is completely contained inside u naught. Yeah. So for j very large, we will since our xnj is converged to x naught, xnj is going to belong to b epsilon by 2 x naught, right? So we can take the ball of radius epsilon by 2 around x naught, right? So we can take this to be xnj. So we can choose j large so that 1 upon nj is strictly less than epsilon by 2, right? Then it is easily checked. So in fact, so if we take the ball, so x and j is here, right? Our x and j is here. Let's say this is x and j. So if I take a ball of radius epsilon by 2 around x and j, right? So then this ball is also going to be completely contained inside the epsilon ball around x naught, right? So then it is easily checked. Okay, so before that, right? So then the ball of radius 1 upon nj around x and j is contained in the ball of radius epsilon by 2 around x and j, and this ball is going to be completely contained inside the ball of radius epsilon around x naught, okay, which is contained in u naught. Okay, but this contradicts the assumption that b 1 upon nj x and j is not contained in ui for any I, right? So recall that we had constructed this sequence xn's by requiring that they satisfy this condition, but we have now contradicted this condition. Okay, so this proves claim 1. Okay. Now let us prove claim 2. In fact, claim 2 is the main assertion, right? So there is a finite subcover of X. Okay, so let's prove claim 2. Right. So by claim 1, there is a delta such that for every x, b delta x is contained in ui for some I. Right. So thus we have b delta by 2 x is contained in b delta x is contained in ui. Okay. So let's start a process of covering x as follows. So choose any y1 in x and let x1 be equal to b delta by 2 y1. Okay. So our x is like this, and we can just pick any y1 and we take this ball of radius delta by 2 around y1. So let me make this a little. So we choose y1 and we take this ball of radius delta by 2 around y1, right? So assume that. So now choose y2 from x minus x1, right? So we can choose any y2 over here which is not in this ball, and this is y2, and we take the ball of radius delta by 2 around y2, right? And let x2 be equal to b delta by 2 y1 union b delta by 2 y2, right? So assume that we have defined xn defined xn, okay, and define xn plus 1 as follows, right? So we choose any yn plus 1 in x minus xn and let xn plus 1 be equal to b delta by 2 yn, we should yn plus 1 union xn, right? So we have these balls, so we have these balls and this is our yn plus 1, right? So then we have x1 is contained in x2 is contained in x3 and so on, right? So we claim that this process has to stop in finitely many steps. Okay. Why? What happens if it does not stop? If not, then we get a sequence of points yns, right, such that the distance between yi and yj is greater than or equal to delta by 2 for all I not equal to j. Right, this is how the yns have been constructed. We take the open balls of radius delta by 2 around y1 and we chose y2 outside that ball, which means that the distance of y1 from y2 is greater than or equal to delta by 2. Now we take open balls of radius delta by 2 around y1 and y2, took their union, and y3 was selected outside this. That means that the distance of y3 from y1 and y3 from y2 is also greater than or equal to delta by 2, right? and this sequence cannot have a convergent subsequence. Right. So thus this process stops. Right. So this implies that our x is contained in the finite union of b delta by 2 y i's I equal to 1 to some n, right, and each of these b delta i's is contained in some u j equal to 1 to n u I j, right. So this implies that there is a finite subcover which implies x is compact. Right. So this completes the proof of the theorem. So we will end this lecture here.